What lies above and below our solar system will completely change the way you see the universe. Right now, as you watch this video, you are floating through space on a tiny rock, and surrounding you, both above your head and below your feet, are structures so massive and so strange that your brain can barely understand them. We think we know our cosmic neighborhood. We learn about the 8 planets. We hear about the sun. We see pictures of pretty galaxies far, far away. But what most people never hear about are the invisible giants that wrap around our entire solar system, like a dark, frozen shell. And even higher up, beyond anything we can see with our eyes, there is a ghostly halo made of something we cannot touch, cannot smell, and cannot even detect directly. It is called dark matter, and it weighs more than everything you have ever seen in the night sky combined. So let me take you on a journey. We are going to leave Earth behind. We are going to fly past the planets, past the icy objects at the edge of our system, and into the dark spaces that no human has ever visited. And then we are going to go even further. We will rise above the flat disk of our galaxy and look down at the strange forces that hold everything together. By the end of this video, you will understand something that most people never even think about. You will know what truly surrounds us, both above and below, and it will blow your mind. Let us begin by leaving home. Picture yourself standing on Earth. The ground feels solid beneath your feet. The sky above you looks calm and blue, but the truth is, you are already moving faster than you can imagine. Earth is spinning on its axis at about 1,000 miles per hour. At the same time, our whole planet is racing around the sun at nearly 70,000 miles per hour. And the sun itself is not standing still either. It is carrying all of us, every planet, every moon, every asteroid, on a wild ride through the Milky Way galaxy at almost 500,000 miles per hour. You are on a cosmic roller coaster, and you did not even buy a ticket. Now, as we begin our journey outward, the first thing we need to understand is the shape of our solar system. Most people picture it as a flat disk, like a pizza floating in space, and in some ways, that is true. The 8 major planets all orbit the sun in roughly the same flat plane. This plane is called the ecliptic. If you could look at our solar system from the side, you would see the sun in the middle, and all the planets lined up in a thin, flat band around it. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all stay pretty close to this invisible flat surface as they travel around the sun. But here is where things get interesting. The flat pizza shape is only part of the story. It is like looking at a house and only seeing the ground floor. Yes, the ground floor exists. But there is so much more above and below. Our solar system has layers that extend far, far beyond the neat little disk where the planets live. And those layers contain mysteries that scientists are still trying to solve today. To understand what lies below and above our solar system, we first need to travel to the edge. And I do not mean the edge where Neptune orbits. No, Neptune is just the last of the big planets. The true edge of the sun's kingdom is much, much further out. So let us keep flying. We pass Neptune and its strange blue clouds. We wave goodbye to its moon Triton, which orbits backwards compared to most other moons. And then we enter a region that most people have never heard of. It is called the Kuiper Belt. The Kuiper Belt is like a giant ring of frozen leftovers from when our solar system was born. It starts around the orbit of Neptune and stretches outward for billions of miles. Inside this ring, there are millions of icy objects tumbling through the darkness. Some of them are tiny, just a few miles across. Others are big enough to be called dwarf planets. You have probably heard of the most famous one. It used to be called the ninth planet. Its name is Pluto. Pluto lives in the Kuiper Belt, along with its 5 moons. For decades, scientists thought Pluto was special. They thought it was the last outpost before empty space began. But then, starting in the early 2000s, astronomers began finding more and more objects out there in the darkness. They found Eris, which is actually a little more massive than Pluto. They found Makemake, Haumea, and dozens of other frozen worlds. Suddenly, Pluto did not seem so special anymore. It was just one member of a huge family of icy objects living in the Kuiper Belt. But even the Kuiper Belt is not the end of our solar system. Oh no, we have barely scratched the surface. As we fly further outward, the icy objects of the Kuiper Belt become fewer and fewer. The darkness grows deeper. The sun, which looked so bright and warm from Earth, now appears as just another star in the sky. A bright star, yes, but not much bigger than the other points of light surrounding it. Out here, the temperature drops to nearly 400 degrees below zero. Nothing can survive. Nothing can grow. This is a place of eternal cold and silence. And yet, the sun's influence still reaches out here. You see, the sun does more than just shine light. It also blows a constant stream of tiny particles out into space. This stream is called the solar wind. It is like the sun's breath, constantly pushing outward in all directions. The solar wind creates a giant bubble around our entire solar system. This bubble is called the heliosphere. Inside the heliosphere, the sun is in charge. Its wind pushes back against everything that tries to come in from outside. But the solar wind cannot blow forever. Eventually, it runs out of energy. It slows down. It crashes into the stuff that exists between the stars. This is where we find one of the most important boundaries in our solar system. It is called the termination shock. At the termination shock, the solar wind suddenly slows down from supersonic speeds to much slower speeds. It is like a river hitting a wall of rocks. The water does not stop completely, but it slows down dramatically and becomes choppy and turbulent. Beyond the termination shock, there is a region called the heliosphere. This is where the solar wind is still pushing outward, but it is weak and tired. It is mixing with the material from interstellar space. The heliosphere is like a buffer zone between our solar system and the rest of the galaxy. It is a no man's land where the sun's influence is fading but has not quite disappeared. And then, finally, we reach the true edge. It is called the heliopause. This is the point where the solar wind stops completely. Beyond this invisible line, the sun has no more power. The material out there does not come from our star. It comes from other stars, from ancient explosions, from the general soup of gas and dust that fills the spaces between star systems. When you cross the heliopause, you are no longer in the sun's kingdom. You have left home. Only 2 human-made objects have ever crossed this boundary. They are called Voyager 1 and Voyager 2. These brave little spacecraft were launched back in 1977. They flew past Jupiter and Saturn, sending back amazing pictures. Voyager 2 also visited Uranus and Neptune. And then, instead of stopping, they just kept going. They flew out into the darkness, further and further from the sun. In 2012, Voyager 1 became the first human object to enter interstellar space. Voyager 2 followed in 2018. Right now, as you listen to this, both Voyagers are still out there, still sending back weak radio signals, still exploring the unknown. They are more than 14 billion miles from Earth, and they are still going. But here is the thing that will really twist your brain. Even though the Voyagers have left the heliosphere, they have not left the solar system. Not even close. The sun's gravity still reaches much, much further than its wind. And out there, in the darkness beyond the heliopause, there is a structure so vast and so mysterious that it makes everything else we have talked about look tiny. It is called the Oort Cloud, and it is what we mean when we talk about what lies below our solar system. Now, I need to explain what I mean by below. Remember how I said the planets orbit in a flat disk called the ecliptic? Well, the Oort Cloud is different. It is not flat at all. It is a sphere. Imagine a giant bubble surrounding our entire solar system. The planets, the Kuiper Belt, even the heliopause, all of these things are like a tiny dot at the very center of this enormous bubble. The Oort Cloud wraps around everything, above and below and on all sides. Scientists believe the Oort Cloud begins somewhere around 2,000 times further from the Sun than Earth is. To put that in perspective, it takes light about 8 minutes to travel from the Sun to Earth. It takes light about 4 hours to reach Neptune. But to reach the inner edge of the Oort Cloud, light has to travel for almost an entire year. And the outer edge is even further. Some estimates say the Oort Cloud extends nearly 2 light years from the Sun. That is almost halfway to the nearest star. So what is out there in the Oort Cloud? The answer is trillions of icy objects. These are not big planets or dwarf planets. Most of them are small, just a few miles across. They are like dirty snowballs, made of ice and rock and frozen gases. They have been out there since the very beginning of our solar system, more than 4 billion years ago. When the planets were forming closer to the Sun, these icy objects got kicked outward by the gravity of the giant planets. Jupiter especially was like a bully, using its massive gravity to fling these small objects into the far reaches of space. And there they have stayed, frozen and forgotten ever since. But here is where it gets really interesting. Every now and then, something disturbs the Oort Cloud. Maybe a passing star gets a little too close. Maybe the gravity of the entire galaxy gives the cloud a gentle tug. When this happens, some of those icy objects get knocked out of their peaceful orbits. They start falling toward the Sun. And when they get close enough, something magical happens. The ice begins to heat up. It starts to turn into gas. A tail forms behind the object, stretching millions of miles across space. We call these objects comets. Long-period comets are the visitors from the Oort Cloud. These are the comets that take thousands or even millions of years to complete one orbit around the Sun. When you see a bright comet in the night sky, one that has never been recorded in human history before, it probably came from the Oort Cloud. It spent billions of years out there in the darkness, and now, for a brief moment, it is visiting the inner solar system. It swings around the Sun, puts on a beautiful show, and then heads back out into the cold. We might never see it again. The Oort Cloud is so far away and so dark that we have never actually seen it. No telescope on Earth or in space can spot those tiny frozen objects at such enormous distances. We only know the Oort Cloud exists because of the comets it sends our way. Scientists have studied the orbits of long-period comets and worked backward to figure out where they must be coming from. The math points to a giant sphere of icy objects surrounding our entire solar system, but we have never taken a picture of it. We have never sent a spacecraft there. The Oort Cloud remains one of the greatest mysteries in our cosmic backyard, and the mysteries only get deeper when we consider what else might be hiding out there. You see, the Oort Cloud is so vast and so unexplored that it could contain things we have not even imagined yet. Some scientists have suggested that there might be larger objects out there, not just small icy chunks, but actual planets. Maybe there are rogue planets, worlds that formed around other stars and got ejected into space, and then got captured by our sun's gravity. These wandering worlds could be floating through the Oort Cloud right now, completely invisible to us. There is even a theory about a hidden planet in our own solar system. Scientists call it Planet 9. The idea came from studying the orbits of some strange objects in the outer solar system. These objects all seem to be clustered together in a weird way, as if something massive is pulling on them. Some astronomers believe a large planet, maybe 5 to 10 times the mass of Earth, could be hiding out there in the darkness. It would be so far from the sun and so dim that our telescopes have not found it yet, but its gravity might be shaping the outer solar system in ways we can detect. Imagine that, a planet bigger than Earth, part of our own solar system, and we do not even know if it exists. The Oort Cloud and the outer solar system hold secrets we are only beginning to understand. And all of this exists below us, in the sense that it wraps around the entire system in a giant sphere, extending far beneath the plane where the planets orbit. But let us not forget the darkness itself. The space inside the Oort Cloud is not completely empty. Between all those icy objects, there is a thin soup of gas and dust. Some of this material came from our own solar system. Some of it drifted in from interstellar space. And some of it might contain clues about the chemistry that makes life possible. Scientists have found complex organic molecules floating in space. These are the building blocks of life, just drifting through the void. The Oort Cloud might be a giant freezer, preserving the ingredients that could someday seed life on other worlds. Now, let us talk about one of the strangest objects we have ever found in the outer solar system. Its name is Sedna, and it breaks all the rules. Sedna is a dwarf planet, about 1,000 miles across, covered in red ice. It was discovered in 2003, and immediately, scientists knew something was very wrong with its orbit. Most objects in the Kuiper Belt stay relatively close to the plane of the planets, but Sedna goes on a wild journey. Its orbit takes it incredibly far from the sun, almost 1,000 times further than Earth. It takes Sedna about 11,000 years to complete just one trip around the sun. What makes Sedna so strange is that its orbit cannot be explained by the gravity of the known planets. Something else must have shaped its path. Some scientists think a passing star might have pulled on Sedna billions of years ago. Others think it could be evidence for Planet 9. And still others believe Sedna might be an object that originally came from the inner part of the Oort Cloud and somehow got kicked into a weird orbit. Whatever the explanation, Sedna is a reminder that the outer solar system is full of surprises. Since Sedna was found, astronomers have discovered several other objects with similar strange orbits. They have names like Biden, Leleakuhonua, and 2T12 VP113, which some people have nicknamed Biden because of its catalogue number. These objects seem to form a new category, sometimes called inner Oort Cloud objects or sednoids. They live in a region between the Kuiper Belt and the main Oort Cloud, a kind of no man's land that we barely knew existed a few decades ago. Every new discovery out there teaches us something about the history of our solar system. The positions and orbits of these distant objects are like fossils. They preserve information about what happened billions of years ago, when the planets were still forming and the solar system was a chaotic mess of collisions and near misses. By studying the outer solar system, scientists can piece together the story of how we got here. Let us now begin our journey in the other direction. We've explored what lies below, the spherical shell of frozen objects that surrounds our entire system. But what about above? What exists when we leave the solar system and travel upward, away from the flat disk of the Milky Way galaxy? To understand this, we first need to zoom out even further. So far, we have been thinking about the solar system on its own, floating in space. But the truth is, our solar system is just one tiny piece of a much larger structure. We live inside a galaxy called the Milky Way, and the Milky Way contains somewhere between 200 billion and 400 billion stars. Our Sun is just one of them. It is not especially big or bright or special. It is an average star living in an average part of an average galaxy. The Milky Way has a shape. If you could see it from outside, it would look like a flat disk with spiral arms. The disk contains most of the stars, gas, and dust in the galaxy. It is about 100,000 light years across, but only about 1,000 light years thick. Our solar system lives inside this disk, about 27,000 light years from the center. We are not at the center of anything. We are just somewhere in the suburbs, orbiting the galactic core like every other star around us. But the disk is not all there is to the Milky Way. Above and below the flat disk, there is something else. There are structures that extend far beyond the thin plane where most stars live. And the further we go above or below the disk, the stranger things get. First, let us talk about the galactic halo. This is a roughly spherical region that surrounds the entire disk of the Milky Way. The halo contains old stars, globular clusters, and a whole lot of mystery. The stars in the halo are different from the stars in the disk. They are ancient, some of the oldest stars in the entire universe. They formed more than 12 billion years ago, when the galaxy was young and had not yet settled into its current flat shape. Globular clusters are especially fascinating. These are tight balls of stars, containing hundreds of thousands or even millions of stars packed into a relatively small space. They orbit the center of the galaxy, but they do not stay in the disk like most stars do. Instead, they swing above and below the plane on long, looping orbits. There are about 150 known globular clusters in the Milky Way's halo. Each one is like a tiny galaxy unto itself, full of ancient suns that have been burning for almost as long as the universe has existed. But the stars and clusters in the halo are just a tiny part of what exists up there. Most of the halo is made of something we cannot see at all. It is called dark matter, and it is one of the biggest mysteries in all of science. Here is the problem. When astronomers study galaxies, including our own, they measure how fast things are moving. They look at how far stars orbit the center of the galaxy. They look at how fast the galaxy rotates, and then they use the laws of physics to calculate how much mass the galaxy must have to create that motion. It is like watching a car drive around a curve and figuring out how sticky the road must be to keep it from flying off. When scientists did this calculation for the Milky Way and other galaxies, they got a shocking result. There is not enough visible matter to explain the motion they observe. The stars, gas, and dust that we can see with our telescopes only account for about 15% of the mass that should be there. The other 85% is invisible. It does not emit light. It does not absorb light. It does not interact with normal matter in any way we can detect directly. But its gravity is definitely there, pulling on stars and shaping the galaxy. Scientists call this invisible stuff dark matter. We do not know what it is made of. We have never captured a particle of dark matter in a laboratory, but we know it exists because of its gravitational effects. And most of this dark matter is concentrated in the halo, in a giant invisible sphere that surrounds the entire galaxy. Try to imagine this. The beautiful spiral disk of the Milky Way that you see in pictures is just the visible part. It is floating inside an enormous ball of dark matter that we cannot see. The dark matter halo extends far above and far below the disk. Some estimates say it reaches out more than 1 million light years from the center of the galaxy. That is 10 times wider than the visible disk. Most of the Milky Way, by mass, is invisible. This is what lies above our solar system in the grandest sense. We are embedded in a sea of dark matter. It flows through the solar system, through the Earth, through your body right now, and you do not feel a thing. Dark matter particles, whatever they are, pass through normal matter like ghosts walking through walls. Billions of them might be streaming through you every second, and you would never know. Scientists have built elaborate experiments to try to catch dark matter particles. Deep underground, shielded from cosmic rays and other noise, they have placed incredibly sensitive detectors. The hope is that every now and then, a dark matter particle might bump into a normal atom and create a tiny signal. So far, no one has definitively caught one. The hunt continues, and it is one of the most important quests in modern physics. But even without knowing exactly what dark matter is, we can study its effects. We know it holds galaxies together. Without dark matter, stars on the outer edges of galaxies would fly off into space. The extra gravity from dark matter keeps everything bound together. We know dark matter shaped the early universe. After the Big Bang, dark matter clumped together first, and then normal matter fell into those clumps, eventually forming stars and galaxies. Without dark matter, we might not exist at all. And here is something even more mind-bending. The dark matter halo around our galaxy is not the end. Looking even further above and below, we find that galaxies themselves are organized into larger structures. The Milky Way is part of a group called the Local Group, which contains about 80 galaxies. The Local Group is part of an even bigger structure called the Virgo supercluster, and the Virgo supercluster is just one piece of an even larger structure called Laniakea, which contains about 100,000 galaxies. All of these structures, from galaxies to superclusters, are connected by filaments of dark matter. If you could somehow see dark matter, the universe would look like a vast cosmic web, with galaxies strung along the strands like dewdrops on a spider web. The spaces between the filaments are enormous voids, nearly empty expanses of nothing. We live in one of the strands, orbiting within the Milky Way, which orbits within the Local Group, which flows along with Laniakea towards some unknown gravitational attractor. But let us bring our focus back to what lies immediately above our solar system. Besides dark matter, there is another invisible force raining down on us from the cosmos. These are cosmic rays, and they are some of the most energetic particles in the universe. Cosmic rays are not actually rays at all. They are particles, mostly protons, flying through space at nearly the speed of light. Some cosmic rays are relatively gentle, coming from our own sun during solar flares, but others are far more powerful. They come from outside our solar system, from outside our galaxy even, carrying energies that dwarf anything we can create on Earth. Where do these super powerful cosmic rays come from? That is one of the great mysteries of astrophysics. Some of them probably come from supernovas, the explosive deaths of massive stars. When a star explodes, it sends shockwaves rippling through space, and those shockwaves can accelerate particles to incredible speeds. Other cosmic rays might come from the regions around black holes, where matter spirals inward and gets heated to extreme temperatures. And the most energetic cosmic rays of all the ones with energies millions of times higher than anything at our particle accelerators, might come from events we do not even understand yet. These cosmic ray particles rain down on our solar system constantly. They come from above, from below, from all directions. Most of them never reach Earth's surface because our atmosphere acts like a shield, absorbing and scattering the incoming particles. But some of them make it through. Every second, about one cosmic ray particle hits every square centimeter of your body. You are being bombarded right now, and you do not feel it because each particle is so tiny. Cosmic rays can be dangerous. They can damage DNA and increase the risk of cancer. This is one of the big challenges for astronauts on long missions. In space, without Earth's atmosphere to protect them, they are exposed to much higher levels of cosmic ray radiation. Future missions to Mars or beyond will need to find ways to shield astronauts from this invisible threat. But cosmic rays are also useful. When they hit Earth's atmosphere, they create showers of secondary particles that rain down to the surface. Scientists can detect these showers and trace them back to figure out where the original cosmic ray came from. By studying cosmic rays, we can learn about the most violent events in the universe, even when those events happened in distant galaxies billions of years ago. So now we have a picture of what lies above and below our solar system. Below us, in the sense of all around us in a spherical shell, is the Oort Cloud, a vast reservoir of frozen objects left over from the birth of the solar system. Beyond that is interstellar space, the cold void between the stars. Above us, in the sense of beyond the flat disk of the galaxy, is the halo, filled with ancient stars, globular clusters, and most importantly, a sea of invisible dark matter. And streaming through everything, from every direction, are cosmic rays, the high-energy messengers from the most extreme events in the cosmos. But we are not done yet. There is still more to explore. Let us talk about the journey our solar system takes through all of this. Because remember, we are not standing still. We are moving, constantly, on a cosmic journey that most people never think about. Our solar system orbits the center of the Milky Way galaxy. One complete orbit takes about 230 million years. This is sometimes called a galactic year. Earth has only completed about 20 trips around the galaxy since it formed. The dinosaurs were alive less than 1 galactic year ago. Humans have been around for barely an eye blink of galactic time. As we orbit, we do not follow a perfectly flat path. The solar system bobs up and down, oscillating above and below the galactic plane. We pass through the dense disk of the galaxy, then rise above it into the sparser halo, then fall back down through the disk and below it, then rise again. This up and down motion takes about 60 million years to complete one full cycle. Why does this matter? Because the environment around our solar system changes depending on where we are in this cycle. When we pass through the dense disk of the galaxy, we encounter more gas, more dust, and more gravitational disturbances. Some scientists have suggested that these passages through the galactic plane might be linked to mass extinctions on Earth. The idea is that increased gravitational tugs from nearby stars might disturb the Oort Cloud, sending more comets toward the inner solar system. More comets means more chances for a big impact, which could wipe out species. This is still a controversial idea, and the evidence is not conclusive. But it is a fascinating possibility that the shape of our galaxy and our journey through it might have played a role in the history of life on Earth. The dinosaurs might have been killed, at least in part, because of where the solar system happened to be in its galactic orbit 66 million years ago. Right now, the solar system is located slightly above the galactic plane, about 65 light-years above the exact midpoint. We are rising higher, and we will reach our maximum height above the disk in about 14 million years. Then we will start falling back, down, passing through the disk again in about 30 million years. This slow cosmic roller coaster never ends. As we travel, we are also passing through what astronomers call the local interstellar cloud. This is a patch of gas and dust about 30 light-years across. Our solar system entered this cloud sometime in the last few thousand years, and we will probably exit it within the next 10,000 to 20,000 years. The local interstellar cloud is relatively warm and diffuse. It presses against the outer boundary of our heliosphere, that protective bubble created by the solar wind. Outside the local interstellar cloud, things are different. The interstellar medium, the stuff between the stars, varies a lot from place to place. Some regions are dense and cold. Others are hot and thin, heated by nearby supernovas. As the solar system travels through the galaxy over millions of years, we pass through different kinds of interstellar environments. These changes might subtly affect conditions on Earth, though the effects are hard to measure. Let us pause here and check in with ourselves. We have traveled so far in this video. We started on Earth, a small rocky planet orbiting an average star. We flew past the familiar planets, through the Kuiper Belt, past the heliopause, and into the theoretical realm of the Oort Cloud. We learned that our solar system is wrapped in a spherical shell of frozen objects that extends nearly halfway to the nearest star. Then we zoomed out even further, past the solar system entirely, and saw our place in the Milky Way galaxy. We discovered that the visible disk of stars is floating inside a much larger invisible halo of dark matter. And we learned that cosmic rays, the fastest particles in the universe, are constantly raining down on us from all directions. What does all of this mean? How should we feel about our place in the cosmos? I think the most honest answer is that it should fill us with awe and a little bit of healthy fear. We are so small. Our solar system, which seems so vast when you try to imagine flying from Earth to Neptune, is just a speck compared to the Oort Cloud. The Oort Cloud, which might extend 2 light-years from the Sun, is tiny compared to the Milky Way. The Milky Way, with its hundreds of billions of stars, is just one galaxy among trillions in the observable universe. And the observable universe might be just a tiny fraction of everything that exists. We are surrounded by forces we barely understand. Dark matter is everywhere, passing through us, shaping galaxies, and we do not even know what it is made of. Cosmic rays bombard us constantly, carrying energies that hint at the most violent events in cosmic history. The Oort Cloud might be hiding planets we have never seen. Our solar system bobs up and down through the galaxy on a journey that takes millions of years. And each part of that journey brings us into contact with different hazards and environments. And yet, here we are. Life exists. On this tiny rock, orbiting this average star, in this quiet corner of the galaxy, something incredible happened. Molecules came together, cells formed. Evolution did its work over billions of years. And now, conscious beings can look up at the night sky and wonder about what lies above and below. That is the mind-blowing part. Not just that the universe is vast and mysterious, but that we can understand even a small piece of it. 100 years ago, we did not know that other galaxies existed. 50 years ago, we had not yet detected the Kuiper Belt. 20 years ago, the first Voyager crossed into interstellar space. Every year, we learn more. Every year, the mysteries get deeper and more fascinating. The Oort Cloud remains out there, waiting to be explored. Maybe someday, centuries from now, human spacecraft will reach it. They will see for themselves what lies in that frozen shell. Maybe they will find Planet 9, or rogue planets, or something we have not even imagined. Maybe they will discover that the Oort Cloud is even stranger than we thought. Above us, dark matter continues to hold the galaxy together. Scientists around the world are working to understand what it is. Maybe in your lifetime, someone will finally catch a dark matter particle and figure out its secrets. That discovery would change physics forever. It would answer one of the biggest questions ever asked about the universe. And cosmic rays keep raining down, bringing messages from exploding stars and feeding black holes. Each particle is a tiny piece of evidence about the most extreme environments in existence. By studying them, we can learn about places we will never visit, events we will never witness directly. So the next time you look up at the night sky, remember what you have learned today. The stars you see are just a tiny part of the story. Above them, invisible and vast, is a halo of dark matter larger than the galaxy itself. Below them, wrapped around our entire solar system, is a shell of frozen objects that has remained unchanged for billions of years. We are swimming in mysteries. We are surrounded by wonders, and that truly is what blows my mind. Not that the universe is big, we all knew that, but that we, tiny creatures on a tiny planet, can figure this stuff out. We can send robots to the edge of interstellar space. We can build detectors to hunt for ghostly dark matter. We can trace the origins of cosmic rays back to supernovas and black holes. We are curious, clever, and stubborn. And the universe, as vast and indifferent as it might be, keeps giving us puzzles to solve. Let me leave you with one final thought. Everything I have described in this video, the Oort Cloud, the heliopause, the dark matter halo, the cosmic rays, all of it exists right now as you watch these words go by. It is not science fiction. It is not a far-off future. It is reality. You are living inside it. The frozen objects of the Oort Cloud are drifting silently above and below you. Dark matter is streaming through your room. Cosmic rays are passing through your body. You are connected to the entire cosmos, whether you think about it or not. But now you do think about it. Now you know, and I hope that knowledge makes you feel something. Maybe wonder, maybe humility, maybe excitement. Whatever you feel, hold on to it. Let it remind you that we are part of something much bigger than ourselves. The solar system is our home, but it sits at the center of a vast, dark, mysterious shell. And that shell floats inside a galaxy wrapped in invisible matter. And that galaxy drifts through a universe filled with forces we are only beginning to understand. But wait, we have only scratched the surface. There is so much more to explore about what lies in these mysterious regions. Let us dive deeper into the strange objects that exist at the edge of our solar system and beyond. You remember we talked about Sedna earlier, that strange red dwarf planet with the crazy long orbit. But Sedna is just one example of a whole category of bizarre objects lurking in the outer solar system. These objects challenge everything we thought we knew about how our cosmic neighborhood formed. And some of them might hold clues to one of the biggest unsolved puzzles in planetary science. Let us talk more about the hunt for Planet 9. This is not some wild conspiracy theory. This is serious science being done by respected astronomers at major universities. The story begins in 2014, when two scientists named Chad Trujillo and Scott Shepard were studying distant objects beyond Neptune. they noticed something strange. Several of these objects had orbits that were clustered together in a suspicious way. Their orbits were all tilted at similar angles and pointed in similar directions. This is weird because the gravitational pull of the known planets should scramble these orbits over time. The fact that they were clustered suggested something else was going on. In 2016, two other scientists, Konstantin Batygin and Mike Brown, took a closer look at this clustering. They ran computer simulations to see what could cause it, and they found that a massive planet, somewhere between 5 and 10 times the mass of Earth, could explain the pattern. This hypothetical planet would orbit far, far from the Sun, maybe 20 times further than Neptune. Its gravity would gently push on the smaller objects, herding them into the clustered orbits we observe. Since then, the hunt for Planet 9 has become one of the most exciting searches in astronomy. Telescopes around the world are scanning the sky, looking for that faint point of light that could be the 9th planet. The problem is that Planet 9, if it exists, would be incredibly dim. It would be so far from the Sun that very little light would reach it, and even less would bounce back to Earth. Finding it is like looking for a specific grain of sand on a beach at night. Some scientists are skeptical. They point out that the clustering might be a statistical illusion. Maybe we are only seeing a biased sample of objects because we can only detect the ones in certain parts of the sky. As we discover more distant objects, the clustering might go away. The debate continues, and only more data will settle it. But imagine for a moment that Planet 9 is real. Imagine that there is a planet bigger than Earth, orbiting in the dark reaches of our solar system, completely invisible to us until just a few years ago. What kind of world would it be? It would be incredibly cold, far colder than Pluto. Any atmosphere it once had might have frozen solid long ago. It might be shrouded in perpetual darkness, lit only by the faint glow of distant stars. No sunlight to speak of, no warmth, just endless cold and silence. And yet, even a world like that could teach us so much. How did it get there? Was it formed in the outer solar system and slowly migrated outward? Or was it born closer to the Sun and got kicked out by gravitational interactions with Jupiter or Saturn? Could it even be a captured rogue planet, a world that was born around another star and wandered through interstellar space until our Sun's gravity caught it? Each of these possibilities tells a different story about the history of our solar system. Speaking of rogue planets, let us talk about these cosmic wanderers in more detail. A rogue planet is a planet that does not orbit any star. It drifts through the galaxy alone, untethered, moving from one star system to another over millions or billions of years. For a long time, scientists thought rogue planets might be rare. After all, we think of planets as things that orbit stars. The idea of a planet without a star seems strange, but recent research suggests rogue planets might be incredibly common. Some studies estimate there could be more rogue planets in the Milky Way than there are stars. Think about that for a moment. Hundreds of billions of planets, maybe trillions, wandering through the darkness with no sun to warm them. They could be everywhere. There might be rogue planets passing through the Oort Cloud right now, and we would have no idea. How do rogue planets form? There are a few possibilities. Many of them probably started out as normal planets orbiting stars. But during the chaotic early days of a solar system, gravitational interactions can eject planets into interstellar space. A close encounter with a giant planet like Jupiter could sling a smaller world right out of the system. The ejected planet would then wander the galaxy forever, a ghost of what it once was. Other rogue planets might form directly from collapsing clouds of gas and dust, similar to how stars form. If a cloud is too small to ignite nuclear fusion, it could collapse into a planet-sized object instead of a star. These would be rogue from birth, never having orbited anything. The thought of rogue planets is both exciting and a little unsettling. They represent a hidden population of worlds we can barely detect. They could be made of rock, ice, or gas. Some might even have moons orbiting them, captured during close encounters with other objects. In the eternal darkness of interstellar space, a rogue planet with a moon would drift silently, two companions in the cosmic void. Could life exist on a rogue planet? At first, this seems impossible. Without a star, there is no sunlight to provide energy. The surface of a rogue planet would be frozen solid, hundreds of degrees below zero. But some scientists have suggested that life might still find a way. If a rogue planet has a thick hydrogen atmosphere, the gas could trap heat from the planet's interior. Radioactive decay in the planet's core might provide enough energy to keep subsurface oceans liquid, and where there is liquid water, there might be life. This is speculative, of course. We have never found life on any world other than Earth. But the possibility that life could exist on a rogue planet, drifting through the darkness between the stars, is one of the most mind-bending ideas in astrobiology. The universe might be filled with hidden habitats we have never even considered. Now, let us return to the structure of our galaxy and look more closely at what it means for our solar system to be embedded in this vast cosmic machine. The Milky Way is not just a random collection of stars. It is a complex, dynamic system with many interconnected parts. Understanding these parts helps us understand our own place in the cosmos. The central feature of the Milky Way is the galactic bulge. This is a dense, roughly spherical collection of stars at the very center of the galaxy. The bulge contains old stars, similar to those in the halo, but packed much more tightly together. At the very heart of the bulge lies one of the most extreme objects in the universe. It is a supermassive black hole, and it has a mass of about 4 million suns. This black hole is called Sagittarius A star, or SGR A star for short. It sits there in the center of our galaxy, about 27,000 light years from Earth. Right now, it is relatively quiet. It is not actively feeding on nearby material, so it does not shine brightly, but we can still detect it by watching how stars near the galactic center orbit. These stars whip around at incredible speeds, clearly being pulled by something massive and invisible. The only thing that could have that much mass in such a small space is a black hole. Every star in the galaxy, including our Sun, orbits around this central black hole. The gravity of the black hole combined with the gravity of all the other stars and dark matter keeps the galaxy together. Without this gravitational glue, the stars would fly apart and the Milky Way would dissolve into a diffuse cloud of wandering suns. The journey of our solar system around the galaxy is a long one. At our current speed, it takes about 230 million years to complete one orbit. This is called a galactic year. Earth is about 4.5 billion years old, so our planet has completed roughly 20 orbits around the galaxy. The dinosaurs went extinct about 66 million years ago, which is less than 1/3 of a galactic year ago. Human civilization is so young that it does not even register on this timescale. As we orbit, we pass through different environments. The Milky Way has spiral arms, regions where stars, gas, and dust are more concentrated. Our solar system is currently located between two spiral arms in a relatively quiet region, but over millions of years, we will pass into and out of spiral arms. These passages might be significant because spiral arms are where most star formation happens. More star formation means more supernovas, which means more cosmic rays and more potential hazards. The spiral arms are not solid structures. They are more like waves moving through the galaxy. Stars do not stay in spiral arms forever. Instead, they pass through them, spending some time in the denser regions before moving back out into the spaces between. Our solar system has probably passed through several spiral arms over its 4.5 billion year history. Let us think more about the dangers that lurk above and below our solar system. We have talked about cosmic rays, but there are other threats too. One of the most dramatic is the gamma ray burst. A gamma ray burst is an incredibly intense flash of gamma radiation, the most energetic form of light. These bursts can release more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. Gamma ray bursts come from the most extreme events in the universe. Some are caused by the collapse of massive stars into black holes. Others might result from the collision of two neutron stars. When these events happen, they produce beams of gamma rays that shoot out into space. If one of these beams happened to be pointed at Earth, the results could be catastrophic. A nearby gamma ray burst could strip away Earth's ozone layer, exposing life to deadly ultraviolet radiation from the Sun. It could trigger mass extinctions on a global scale. Some scientists have even suggested that a gamma ray burst might have caused one of the major extinction events in Earth's history, though this remains unproven. The good news is that gamma ray bursts are rare, and the chances of one happening close enough to harm Earth are very small. Most gamma ray bursts occur in distant galaxies, billions of light years away. By the time their radiation reaches us, it has spread out and weakened to the point of being harmless. But the universe is full of violent events, and we are not immune to their effects. Living in a galaxy means living with a certain amount of cosmic risk. Another potential threat comes from nearby stars. Our Sun is relatively isolated right now, with the nearest star, Proxima Centauri, about 4 light years away. But this will not always be the case. Stars are constantly moving, and over millions of years, some will pass closer to our solar system. About 70,000 years ago, a small red dwarf star called Scholz's star passed through the outer reaches of the Oort Cloud. It came within about 50,000 times the distance from Earth to the Sun, which sounds like a lot, but in cosmic terms, it is a very close call. Scholz's star likely disturbed some of the icy objects in the Oort Cloud, possibly sending some of them tumbling toward the inner solar system. We might not see the effects of this passage for thousands or even millions of years, when comets from that disturbance finally reach the inner planets. In about 1 million years, another star called Gliese 710 will pass even closer. Current estimates suggest it will come within about 10,000 times the Earth-Sun distance, plowing right through the outer Oort cloud. This close encounter will almost certainly disturb the cloud significantly, potentially sending a shower of comets into the inner solar system. Our distant descendants, if humanity still exists, will have to deal with an increased impact risk. These stellar close encounters happen every few million years. The Oort cloud is constantly being stirred and jostled by passing stars. This is one reason why comets continue to fall toward the Sun even after billions of years. The Oort cloud is not a static frozen reservoir. It is a dynamic population, constantly being influenced by the gravitational tides of the galaxy. Speaking of galactic tides, this is another force that affects the Oort cloud. The gravity of the entire Milky Way, concentrated mostly toward the galactic center, creates a tidal effect on objects in the outer solar system. This tidal force is very gentle, but over millions of years it adds up. It can slowly change the orbits of Oort Cloud objects, sometimes sending them closer to the Sun. The galactic tide is one of the main reasons why long-period comets exist. Without it, and without passing stars, the Oort Cloud objects might stay frozen in place forever. Now let us explore another fascinating aspect of what lies above, the solar system. We have talked about dark matter, but there is another mysterious component of the universe that pervades everything, including the space above and below our system. It is called dark energy, and it is even stranger than dark matter. Dark energy is not really a thing that exists in the halo or around the solar system in a localized way. It is more like a property of space itself. Dark energy is causing the expansion of the universe to accelerate. Distant galaxies are moving away from us faster and faster over time, pushed apart by this mysterious force. We do not understand dark energy at all. We do not know why it exists or what causes it. But observations of distant supernovas and the cosmic microwave background radiation show that dark energy makes up about 68% of the total energy content of the universe. Combined with dark matter at about 27%, this means that the ordinary matter we can see, the stars, planets, gas and dust, makes up only about 5% of everything. Let that sink in. Everything you have ever seen, every star in the sky, every galaxy in the most powerful telescope images, represents just 5% of the universe. The other 95% is invisible, mysterious, and barely understood. We are not just surrounded by the unknown, we are drowning in it. The effects of dark energy are not noticeable on small scales like the solar system or even the galaxy. Gravity is much stronger than dark energy at these scales, so it dominates. But on the larger scales, where gravity is weak because everything is so spread out, dark energy takes over. It is pushing galaxy clusters apart and accelerating the expansion of space itself. In the far distant future, dark energy will have dramatic consequences. If it continues to accelerate the expansion of the universe, eventually distant galaxies will be moving away from us faster than the speed of light. When that happens, their light will never reach us. They will fade from view, crossing an invisible horizon beyond which no information can travel. The universe will become darker and lonelier, with each galaxy isolated in its own little bubble of space. But do not worry, this will take billions of years. The sun will burn out and die long before dark energy becomes a problem for anyone in our solar system. Still, it is humbling to know that even the stable-seeming universe we observe today is changing, expanding, and evolving on timescales we can barely comprehend. Let us shift our focus now and talk about what the regions above and below the solar system can teach us about the history of the universe itself. The Oort Cloud, the halo, and the dark matter that surrounds everything are like time capsules, preserving information about events that happened billions of years ago. The objects in the Oort Cloud are remnants from the birth of our solar system. They formed about 4.5 billion years ago, in the same cloud of gas and dust that gave rise to the sun and planets. But while the planets were subjected to heat, radiation, and geological activity, the Oort Cloud objects have remained frozen and unchanged. They are some of the most primitive materials in the solar system, samples of the original ingredients that went into making everything else. When a comet from the Oort Cloud falls toward the sun and develops its characteristic tail, scientists get excited. That comet is carrying material that has been in deep freeze since before Earth existed. By studying the comet's composition, we can learn about the chemistry of the early solar system. We can find out what kinds of molecules were floating around in space when the planets were forming. Some comets contain organic compounds, the building blocks of life. This has led to the tantalizing idea that comets might have delivered some of the raw materials for life to the early Earth. Similarly, the ancient stars in the galactic halo are windows into the early universe. These stars formed more than 12 billion years ago, when the universe was young and very different from today. By studying their composition, astronomers can learn about the conditions that existed shortly after the Big Bang. The oldest stars have very few heavy elements because those elements had not been created yet. Heavy elements like carbon, oxygen, and iron are forged in the cores of stars and spread through space when those stars explode. The first generation of stars had to work with only hydrogen and helium, the elements left over from the Big Bang itself. Finding and studying these ancient stars is challenging because most of them are faint and far away, but they are out there, in the halo above and below the galactic disk, orbiting the Milky Way on long, looping paths. Each one is a fossil from a time when galaxies were just beginning to form, and the universe was a wildly different place. Dark matter also carries information about the early universe. The distribution of dark matter today reflects how matter clumped together in the first few 100 million years after the Big Bang. By mapping dark matter through gravitational lensing and other techniques, astronomers can learn about the initial conditions that led to the universe we see today. The patterns in the dark matter distribution are like fingerprints of the early cosmos. Let us now consider the sheer scale of what we have been discussing. Numbers can become meaningless when they get too big, so let me try to put some of this in perspective. If you could travel at the speed of light, the fastest speed possible in the universe, it would take you about 4 hours to reach Neptune from the Sun. Getting to the heliopause, where the Voyager spacecraft crossed into interstellar space, would take about 18 hours, but reaching the inner edge of the Oort Cloud would take almost a year. And the outer edge, nearly 2 years of traveling at the speed of light. Of course, we cannot travel at the speed of light. Our fastest spacecraft, Voyager 1, is moving at about 38,000 miles per hour. At that speed, it would take about 300 years to reach the inner Oort Cloud and about 30,000 years to reach the outer edge. Voyager 1 will pass through the Oort Cloud eventually, but it will be a very long journey. Now zoom out further. The Milky Way galaxy is about 100,000 light years across. That means light takes 100,000 years to travel from one side to the other. Our solar system is about 27,000 light years from the center, and the dark matter halo extends even further, perhaps 1,000,000 light years or more from the galactic center. The scale is almost impossible to grasp. And yet, even the Milky Way is just one galaxy among trillions. The observable universe is about 93 billion light years across. It contains more stars than there are grains of sand on every beach on Earth. And beyond the observable universe, there might be even more, perhaps an infinite amount more, that we can never see because light has not had time to reach us. In all of this vastness, Earth is a single point. The solar system is a tiny bubble. The Oort Cloud, which seems so enormous from our perspective, is barely a speck compared to the galaxy. And the galaxy is just one island in an infinite cosmic sea. This is what lies above and below the solar system. Not just the physical structures we have discussed, but the sheer, overwhelming scale of it all. We are tiny beyond comprehension, existing for an eye blink of cosmic time, on a small rock circling an ordinary star. And yet, somehow, we are aware of it. We can think about these distances and timescales. We can send spacecraft to the edge of interstellar space. We can detect the invisible dark matter that holds galaxies together. Our minds, evolved to track predators on an African savanna, are capable of contemplating the structure of the entire universe. That is perhaps the most mind-blowing thing of all. Not the Oort Cloud, not the dark matter halo, not the cosmic rays, or the gamma ray bursts, or the rogue planets wandering through interstellar space. The most mind-blowing thing is that you are here, right now, thinking about all of this. A collection of atoms, briefly conscious, pondering its own place in the cosmos. Let us talk about what the future might hold for our exploration of these regions. Right now, we are limited by technology. Our spacecraft are slow, our telescopes are imperfect, and our understanding is incomplete. But this will not always be the case. Future space missions might be designed specifically to explore the outer solar system and beyond. The Voyager spacecraft were not meant to study the Oort Cloud. They were built to visit the giant planets, and they just happened to keep going. But someday, we might send probes that are designed from the start to travel into the outer darkness. These probes might use new propulsion technologies that we are only beginning to develop. One promising idea is the solar sail. A solar sail is a giant thin sheet of reflective material that uses the pressure of sunlight to accelerate. In principle, a solar sail could achieve much higher speeds than a traditional rocket because it does not need to carry fuel. The farther from the sun it gets, the less effective the sail becomes, but it could still reach the outer solar system faster than anything we have built so far. Another idea is nuclear propulsion. Instead of chemical rockets, which are limited by the energy content of their fuel, a nuclear-powered spacecraft could generate much more thrust. Some designs use nuclear fission, the same process that powers nuclear power plants. Others envision nuclear fusion, the process that powers the sun. A fusion-powered spacecraft could, in theory, reach a significant fraction of the speed of light, though we are a long way from building such a thing. There are even more exotic proposals. Some scientists have suggested using lasers to accelerate lightweight probes to incredible speeds. The Breakthrough Starshot project, for example, is studying the possibility of sending tiny gram-scale spacecraft to nearby stars using powerful ground-based lasers. These probes could potentially reach 10 to 20% of the speed of light, allowing them to reach the nearest star system in about 20 years. A similar approach might one day be used to explore the Oort Cloud. Telescopes are also improving. The James Webb Space Telescope, launched in 2021, is already revolutionizing our understanding of the distant universe. But future telescopes will be even more powerful. Plans are underway for giant ground-based telescopes that will dwarf anything currently in operation. These instruments might be able to detect Oort Cloud objects directly, something we cannot do today. In the coming decades, we might also make progress on detecting dark matter. New experiments, more sensitive than anything currently running, are being designed. If dark matter particles have even the tiniest interaction with normal matter, eventually we will find them. And when we do, it will open up an entirely new chapter in physics. The search for Planet 9 continues as well. If it exists, improved surveys of the sky should eventually find it. The Vera Rubin Observatory, currently under construction in Chile, will scan the entire visible sky repeatedly, looking for faint, moving objects. It is designed to find exactly the kind of distant, dim object that Planet 9 would be. Within the next decade, we should have a definitive answer about whether Planet 9 is real. All of this exploration is driven by curiosity, the same impulse that led our ancestors to explore new lands and cross unknown seas. We want to know what is out there. We want to understand our place in the universe. And with every new discovery, we get a little closer to answering those big questions. What is the ultimate fate of the solar system? Eventually, the sun will exhaust its nuclear fuel. In about 5 billion years, it will swell into a red giant, engulfing Mercury and Venus and possibly Earth. Then it will shed its outer layers and collapse into a white dwarf, a dense remnant no bigger than Earth, but with half the sun's mass. The planets that survive will continue orbiting the dead sun, frozen and dark. The Oort Cloud will likely survive this transformation, at least in part. Some objects will be ejected as the sun loses mass, but others will remain bound. For billions of years after the sun dies, the Oort Cloud will continue to exist, a frozen shell around a stellar corpse. Eventually, even the white dwarf will cool and fade. Over trillions of years, it will become a black dwarf, a completely cold and dark object. The solar system will be a graveyard, filled with frozen planets and icy debris, orbiting a dead star in a dying universe. But that is in the unimaginably distant future. Right now, the sun is shining, Earth is alive, and we have so much left to explore. The Oort Cloud awaits. The dark matter halo surrounds us. Cosmic rays continue to rain down. And somewhere out there, maybe, Planet 9 orbits in silence, waiting to be found. What lies above and below the solar system? Everything. The answer is everything. The entire universe wraps around our little corner of space, from the frozen comets of the Oort Cloud to the invisible dark matter that holds galaxies together. We are surrounded by mystery, and that is what makes it so exciting. The journey we have taken in this video only scratches the surface. There is so much more to learn, so much more to discover. The universe is not a static place. It is changing, evolving, and revealing new secrets all the time. Every year, astronomers find new objects in the outer solar system. Every year, physicists get closer to understanding dark matter and dark energy. Every year, we take one more step into the unknown. I hope this video has given you a new appreciation for the cosmos. I hope it has made you think about the scale of the universe and our place within it. And I hope it has filled you with wonder, because wonder is what drives us to explore. Without wonder, we would stay on Earth forever, never looking up, never asking questions. But with wonder, there is no limit to what we can achieve. So keep looking up, keep asking questions, keep wondering about what lies above and below. The universe is waiting for you. And now, as we wrap up this journey, let me ask you one more time. What fact from this video surprised you the most? Was it the vastness of the Oort Cloud, stretching nearly halfway to the nearest star? Was it the invisible dark matter that makes up most of the mass in our galaxy? Was it the cosmic rays that are passing through your body right now? Or was it something else entirely? Drop a comment below and let me know. I read every single comment, and I love hearing what you think. If you enjoyed this video, please hit that like button. It helps more people find this content and join our community of curious minds. And if you have not subscribed yet, what are you waiting for? Hit that subscribe button and turn on notifications so you never miss a new video. Thank you for watching. Thank you for being curious. And thank you for taking this journey with me to the edges of the solar system and beyond. Until next time, keep exploring, keep wondering, and never stop looking at the stars. But before you go, let me take you even deeper into some of the most fascinating details about these cosmic structures. We have covered the big picture, but the small details are where the real magic lies. Let us return to the Oort Cloud and think about what it would actually be like to travel there. Imagine you are an astronaut on a mission to the outer solar system. You leave Earth on a spacecraft powered by advanced propulsion, something far beyond what we have today. For the first few hours, you watch Earth shrink behind you. The blue marble becomes a small dot, then disappears entirely. The sun is still bright and warm in your windows. Days pass. You fly by the moon, then Mars. Jupiter looms ahead, a giant striped ball with its famous red spot. You swing around it, using its gravity to boost your speed. Saturn comes next, with its beautiful rings. You marvel at the golden clouds and the dozens of moons. Then Uranus, tilted on its side, a pale blue-green world. Finally Neptune, dark blue and stormy, with winds faster than anything on Earth. But Neptune is just the beginning of your journey. You keep going. The Kuiper Belt stretches before you, a vast field of icy debris. You spot Pluto in the distance, a small reddish world with a heart-shaped feature on its surface. You pass it by without stopping. There are other objects here too, thousands of them, tumbling slowly in the darkness. Eris, Makemake, Haumea. You see them as faint dots against the black sky. The sun is getting smaller now. It still outshines everything else in the sky, but it looks less like a sun and more like a very bright star. The temperature outside your spacecraft has dropped far below anything on Earth. Even with the best insulation, you can feel the cold pressing in. This is one of the most isolated places in the known universe. Weeks become months, months become years. You are still flying outward, but the scenery barely changes. Just empty space, black and cold and silent. The stars do not move because they are so far away. The sun continues to shrink. Eventually, it looks no different from the other bright stars around it. You could lose track of which one is home. This is the psychological challenge of deep space travel. The emptiness is overwhelming. There is nothing to see, nothing to hear, nothing to do but wait. The distance stretches your mind in ways you never expected. You start to understand, really understand, how vast the universe is. You are a tiny spark of life in an ocean of nothing. After many years, you finally reach the inner edge of the Oort Cloud, but there is no obvious boundary. No sign that says welcome to the Oort Cloud. The transition is gradual. You just start noticing more objects around you. They are small, most of them, just a few miles across. They are so spread out that you could fly for days without seeing one. But they are there, trillions of them, forming a vast spherical shell around everything you have ever known. You pick one to study up close. Your spacecraft approaches slowly. The object is a frozen mix of ice and rock, dark and ancient. It has not changed in billions of years. You are looking at a piece of the original solar system, a time capsule from before the planets formed. You take samples, you run tests. The data will revolutionize our understanding of how solar systems form, but you cannot stay forever. Your supplies are limited. Your time is running out. You turn your spacecraft around and begin the long journey home. It will take years, maybe decades. You watch the Oort Cloud object shrink behind you, knowing you will probably never see anything like it again. You are returning to the inner solar system, to the light and warmth of the sun. But you will never forget what you saw out there in the darkness. This is science fiction, of course. No human being has ever traveled to the Oort Cloud, and no one will for many generations. But thinking about it helps us understand what these places are really like. They are not just numbers on a page. They are real places, unimaginably cold and dark, waiting for us to explore them. Now let us think about the dark matter halo from a different angle. We have talked about what dark matter is, or rather, what we think it might be. But let us consider what it would mean if we finally figured it out. Right now, dark matter is one of the biggest mysteries in physics. We know it exists because of its gravitational effects, but we do not know what it is made of. The leading candidates are particles called WIMPs, which stands for weakly interacting massive particles. These are hypothetical particles that have mass but do not interact with light or normal matter, except through gravity and possibly the weak nuclear force. If WIMPs exist, they would be passing through everything all the time. Billions of them could be streaming through your body every second, and you would never notice. They are like ghosts, sharing space with us, but utterly invisible. The experiments searching for dark matter are trying to catch one of these ghosts. They use incredibly sensitive detectors, shielded from cosmic rays deep underground, waiting for the rare moment when a dark matter particle bumps into a normal atom. So far, no one has definitively caught a WIMP. This does not mean WIMPs do not exist. It might mean they are even more weakly interacting than we thought, making them harder to detect. Or it might mean dark matter is something else entirely. There are other candidates, like axions, which are much lighter particles that would behave differently. There are also more exotic ideas, like primordial black holes, tiny black holes that formed in the early universe and have been drifting through space ever since. Whatever dark matter turns out to be, discovering it will transform our understanding of the universe. It will be one of the greatest scientific achievements in history, comparable to the discovery of electrons or the structure of DNA. And it will happen eventually. The hunt continues, and with every negative result, we learn more about what dark matter is not, narrowing down the possibilities. The implications go beyond just knowing what dark matter is made of. If we understand dark matter, we might be able to interact with it in new ways. We might find uses for it that we cannot even imagine today. Or we might discover that dark matter is connected to other mysteries, like the nature of gravity or the origin of mass. Physics is full of surprises, and dark matter is likely to provide some of the biggest. Let us also explore the cosmic rays in more detail. We mentioned that they are high-energy particles raining down on us from space, but the story is much richer than that. Cosmic rays were discovered in 1912 by a physicist named Victor Hess. He flew a balloon high into the atmosphere with instruments designed to measure radiation. What he found was surprising. The radiation increased with altitude, not decreased. This meant the radiation was coming from space, not from Earth. Hess had discovered cosmic rays, and he eventually won the Nobel Prize for it. Since then, we have learned a lot about cosmic rays. Most of them are protons, the nuclei of hydrogen atoms. But some are heavier nuclei, like helium, carbon, or even iron. They come from all directions, though the highest energy ones tend to come from outside our galaxy. The energies of cosmic rays span an enormous range. The most common ones have energies comparable to a flying mosquito, which might not sound like much. But these energies are concentrated in a single subatomic particle, which makes them incredibly powerful on a per-particle basis. The highest energy cosmic rays ever detected have energies millions of times higher than anything we can produce at our particle accelerators. These ultra-high energy cosmic rays are among the most energetic things in the universe. Where do these extreme cosmic rays come from? This is one of the great mysteries of astrophysics. To accelerate a particle to such enormous energies requires incredibly powerful magnetic fields and vast distances. Supernovas can produce some cosmic rays, but probably not the most extreme ones. Active galactic nuclei, the regions around supermassive black holes that are actively feeding, are another possibility. Gamma-ray bursts might contribute as well. The truth is, we do not know for sure. The sources of the highest energy cosmic rays remain hidden. When a cosmic ray hits Earth's atmosphere, it does not just pass through. It collides with an air molecule and creates a cascade of secondary particles. This cascade, called an air shower, can contain millions or even billions of particles that rain down over a wide area. Scientists detect these air showers using arrays of detectors spread across large areas. By measuring where the particles land and how much energy they carry, researchers can work backward to figure out the energy and direction of the original cosmic ray. The Pierre Auger Observatory in Argentina is the largest cosmic ray detector in the world. It covers an area larger than the state of Rhode Island, with thousands of individual detectors spread across the landscape. It has been operating since 2004 and has detected some of the most extreme cosmic rays ever recorded. Data from Auger is helping us understand where these particles come from and how they get their incredible energies. Cosmic rays are not just a curiosity, they have practical effects on Earth. When cosmic rays hit the atmosphere, they create isotopes like carbon-14, which scientists use for radiocarbon dating. They also create some of the background radiation that everything on Earth is exposed to. At high altitudes, like when you are flying in an airplane, you receive a higher dose of cosmic ray radiation. Astronauts in space receive even more. Understanding cosmic rays is important for protecting people who travel and work in space. There is also a beautiful connection between cosmic rays and cloud formation. When cosmic rays pass through the atmosphere, they ionize air molecules, creating charged particles. These charged particles can serve as seeds for water droplets to form around. Some scientists have proposed that changes in cosmic ray intensity, driven by solar activity, might affect cloud cover and thus Earth's climate. This is controversial and not fully settled, but it is an example of how the cosmic environment might influence our everyday world in subtle ways. Let us now take a moment to appreciate the explorers who have pushed the boundaries of our knowledge about the outer solar system. The Voyager missions are the most famous, but there have been others, and more are planned. Voyager 1 and Voyager 2 were launched in 1977, taking advantage of a rare alignment of the outer planets that allowed a spacecraft to visit multiple worlds using gravity assists. Voyager 2 visited all 4 giant planets: Jupiter, Saturn, Uranus, and Neptune. A feat that has never been repeated. Both spacecraft continue to operate today, sending back data from interstellar space more than 45 years after their launch. The New Horizons mission, launched in 2006, gave us our first close-up look at Pluto in 2015. The images it sent back revealed a complex, geologically active world, with mountains of frozen nitrogen and a thin atmosphere. After passing Pluto, New Horizons continued into the Kuiper Belt, where it flew by a small object called Arakoth in 2019. Arakoth looks like 2 lobes stuck together, a snowman shape that tells us something about how Kuiper Belt objects formed. New Horizons is still operational and heading outward. It will not reach the Oort Cloud in any of our lifetimes, but it continues to study the outer solar system environment, measuring particles and fields in regions never before explored by spacecraft. Future missions are being planned. Concepts exist for a dedicated interstellar probe that would travel farther and faster than Voyager. Such a mission could study the heliosphere from outside, looking back at our solar bubble from interstellar space. It could measure the properties of the interstellar medium directly, and it might even be able to detect Oort Cloud objects along the way. Other proposed missions would focus on specific targets. a spacecraft to Neptune and its moon Triton, has been discussed for years. Triton is thought to be a captured Kuiper Belt object, so studying it could teach us about the outer solar system. There are also proposals to visit Uranus, the only giant planet that has never had a dedicated mission. Both planets are fascinating and understudied, and they would reveal much about the processes that shaped our solar system. The technology needed for these missions is advancing. Better power sources, like improved nuclear batteries, could keep spacecraft operating for decades. Advanced propulsion systems could reduce travel times. Better instruments could gather more data from greater distances. The outer solar system is not easy to explore, but it is not impossible. With continued investment and ingenuity, we will learn more about what lies at the edge of our cosmic home. Let us reflect on what all of this means for us as human beings. We live on a small planet in a vast universe. We are surrounded by mysteries we are only beginning to understand. The Oort Cloud, the dark matter halo, the cosmic rays. These are not just abstract concepts. They are real features of the cosmos we inhabit. They shape the environment we live in, even if we do not notice them in our daily lives. Understanding these things gives us perspective. It reminds us that our problems, as important as they seem, are small compared to the scale of the universe. It reminds us that we are part of something much bigger than ourselves, and it inspires us to keep exploring, keep questioning, keep searching for answers. Science is one of the greatest achievements of humanity. It is our way of understanding the universe we live in, and the story of what lies above and below the solar system is one of the most exciting chapters in that ongoing adventure. Every generation learns more than the one before. Every decade brings new discoveries. Who knows what we will find next? Maybe we will discover Planet 9 and add a new member to our solar family. Maybe we will catch a dark matter particle and solve one of the biggest puzzles in physics. Maybe we will find evidence of life, past or present, somewhere else in the solar system. Or maybe we will discover something completely unexpected, something no one has even thought of yet. That is the beauty of exploration. We do not know what we will find until we look. And when we look, the universe never fails to surprise us. It is stranger and more wonderful than anything we could have imagined. And it is waiting for us above and below in every direction we choose to explore. So as you go about your day, remember what you have learned here. Remember the Oort Cloud, that vast shell of frozen objects surrounding everything you know. Remember the dark matter halo, the invisible scaffolding that holds galaxies together. Remember the cosmic rays, the high-energy messengers from the most violent events in the cosmos. Remember that you are floating on a small rock, hurtling through space, surrounded by wonders beyond counting. And most importantly, remember to keep looking up. The universe is beautiful. It is mysterious. It is calling to us. And one day, maybe not in our lifetimes, but someday, we will answer that call. We will send humans to the outer solar system. We will unlock the secrets of dark matter. We will understand where cosmic rays come from. We will explore the galaxy and beyond. That is the human spirit. We are curious. We are brave. We are never satisfied with what we already know. We always want to learn more. And that drive, that insatiable curiosity, is what makes us special. In a universe filled with lifeless rocks and empty void, we are a spark of consciousness, trying to understand it all. What lies above and below the solar system? The answer, as we have seen, is vast and complicated. It includes frozen comets and invisible matter and energetic particles and rogue planets and ancient stars. It includes mysteries we have not solved and wonders we have not discovered. It includes everything and nothing, darkness and light, the known and the unknown. But perhaps the most honest answer is this: what lies above and below the solar system is the same thing that lies within us. A universe trying to understand itself. Atoms that somehow became alive, became conscious, and now look out at the cosmos and ask why. We are the universe experiencing itself. And every time we learn something new about the Oort Cloud or dark matter or cosmic rays, we learn something new about ourselves. That is the real mind-blowing truth. Not just that the universe is big and strange, but that we are part of it. We are made of the same stuff as stars and comets and dark matter halos. We are connected to everything, from the smallest particle to the largest structure. And when we explore the cosmos, we are exploring ourselves. So thank you for joining me on this journey. Thank you for letting me share these wonders with you. And thank you for being a fellow explorer in this vast and beautiful universe. If this video has inspired you to learn more, I encourage you to keep exploring. Read books about astronomy. Watch documentaries about space. Visit museums and planetariums. The universe is right there waiting for you to discover it. You do not need a spacecraft to explore the cosmos. You just need curiosity and wonder. Hit that like button if you enjoyed this video. Subscribe if you want to see more. Leave a comment with your thoughts. And most importantly, keep looking up. The stars are calling, the mysteries are waiting, and the adventure is just beginning. Until next time, this has been a journey through what lies above and below the solar system. Stay curious, stay humble, and never stop wondering. The universe is full of surprises, and the best ones are still waiting to be found. Goodbye for now, and clear skies. Actually, wait. I want to share a few more fascinating details before we part ways. There is so much more to say about these incredible cosmic structures, and I would be doing you a disservice if I did not cover them. Let us talk about the interstellar medium, the space between the stars that our solar system is traveling through. This is not empty vacuum. It is a thin soup of gas and dust, mostly hydrogen and helium, with traces of heavier elements. The density is incredibly low, about 1 atom per cubic centimeter in most places. For comparison, the air you are breathing contains about 10 to the 19th power molecules per cubic centimeter. The difference is staggering. Despite being so sparse, the interstellar medium is not uniform. It has structure. There are dense molecular clouds where stars are born. There are hot bubbles blown out by supernovas. There are streams of gas flowing between the spiral arms. Our solar system happens to be passing through a relatively warm, low-density region called the local bubble. This bubble was probably created by a series of supernova explosions that happened millions of years ago, sweeping away the surrounding gas and dust. Within the local bubble, there are smaller structures. The local interstellar cloud that I mentioned earlier is one of them. It is a wispy patch of partially ionized gas that our solar system is currently moving through. The interaction between the solar wind and this cloud creates the shape of our heliosphere. The heliosphere is not a perfect sphere. It is more like a comet, with a rounded head facing the direction we are traveling and a long tail streaming out behind us. The direction we are traveling through the galaxy is called the apex of the Sun's way. It is located in the constellation Hercules, roughly speaking. We are heading toward that part of the sky at about 12 miles per second, relative to nearby stars. This might seem fast, but at this speed, it would take about 80,000 years to reach the nearest star system, Alpha Centauri. As we travel, The heliosphere plows through the interstellar medium like a ship through water. At the front of the heliosphere, there might be a bow shock, similar to the shock wave in front of a supersonic airplane. For a long time, scientists assumed this bow shock existed, but recent data from the Voyager spacecraft and observations of neutral atoms suggest the situation is more complicated. Our heliosphere might not be moving fast enough relative to the local interstellar medium to create a true shock wave. Instead, there might be a gentler bow wave, more like the ripple in front of a canoe. Understanding the shape and behavior of the heliosphere matters because it affects what reaches the inner solar system. The heliosphere acts as a shield, deflecting incoming cosmic rays and interstellar particles. Without it, Earth would be exposed to more radiation from outside the solar system. The sun's magnetic field and solar wind protect us, even from dangers we barely think about. Let us also discuss the magnetic field of the galaxy itself. Just as Earth has a magnetic field and the sun has a magnetic field, the Milky Way has a galactic magnetic field. This field is much weaker than Earth's, about 1/1,000,000th of the strength, but it extends across vast distances. The galactic magnetic field influences how cosmic rays travel through the galaxy. It bends their paths, causing them to spiral around the field lines. This is why cosmic rays seem to come from all directions rather than from specific sources. They have been scrambled by the magnetic field during their journey. The galactic magnetic field also plays a role in star formation. It helps support giant molecular clouds against gravitational collapse, slowing down the rate at which new stars form. Without the magnetic field, the galaxy might have burned through its gas supply long ago, forming stars too quickly. The field acts as a kind of brake, regulating the pace of stellar birth. Scientists study the galactic magnetic field using a variety of techniques. They measure how radio waves from distant sources are affected by passing through the magnetic field. They study the polarization of light from stars and dust. They even use cosmic rays themselves as probes, since the way cosmic rays propagate depends on the field's structure. Piece by piece, astronomers are mapping the magnetic field of our galaxy, revealing its complex and tangled geometry. Now, let us consider the motion of the Milky Way itself. We have talked about how the solar system moves within the galaxy, but the galaxy is also moving through space. The Milky Way is part of the local group of galaxies, and the local group is falling toward a massive concentration of matter called the Great Attractor. Beyond that, there is an even larger structure called the Shapley supercluster that is also pulling on us. These motions are not obvious from our perspective. When you look at the night sky, everything seems peaceful and still, but in reality, we are hurtling through the cosmos at incredible speeds. The solar system orbits the galaxy at about 500,000 miles per hour. The galaxy moves toward the Great Attractor at about 1.5 million miles per hour, and the expansion of the universe is carrying everything apart at speeds that increase with distance. All of this motion means that our cosmic environment is constantly changing, even if the changes are too slow for us to notice in a human lifetime. The stars we see tonight are not in the same positions they were 1,000,000 years ago. The constellations our ancestors saw are not the same ones our descendants will see. Over time, everything shifts and flows, carried along by gravity and the expansion of space. Let us return to the Oort Cloud one more time and consider how it might have formed. The leading theory is that the objects in the Oort Cloud did not form there. They formed much closer to the Sun, in the region where the giant planets were growing. But as Jupiter, Saturn, Uranus, and Neptune took shape, their powerful gravity flung countless small objects outward. Some were ejected from the solar system entirely, becoming rogue comets, wandering between the stars. Others were thrown into elongated orbits that took them to the outer reaches of the solar system. Over time, the gravity of passing stars and the galactic tide reshaped these orbits. Objects that started in elongated, pancake-shaped orbits were gradually shifted into the spherical distribution we call the Oort Cloud. This process took hundreds of millions of years, but eventually the cloud took shape. It has been there ever since, a silent reservoir of icy bodies waiting in the darkness. Some scientists think the Oort Cloud might contain objects that did not form in our solar system at all. When stars pass close to each other, they can exchange material. It is possible that our Sun captured some icy bodies from other stars billions of years ago, adding them to the Oort Cloud. If this is true, then studying Oort Cloud comets could tell us about the conditions around other stars, not just our own. The first interstellar object we know of was detected in 2017. It was named Oumuamua, a Hawaiian word meaning scout or messenger. Oumuamua was a small, elongated object that passed through our solar system on a trajectory that clearly came from outside. It moved too fast to be gravitationally bound to the Sun. It was a visitor from another star system just passing through. Oumuamua raised many questions. Its shape was unusual, more elongated than any comet or asteroid in our solar system. It showed no signs of outgassing, the release of gas that creates comet tails. Some scientists speculated about exotic explanations, but the most likely answer is that Oumuamua is just a strange natural object, different from what we are used to, but not mysterious in any deeper sense. Since Oumuamua, another interstellar object has been found. Comet Borisov, discovered in 2019, was more obviously a comet, with a visible tail and clear signs of outgassing. It came from interstellar space, passed through the inner solar system, and then headed back out into the void. Studying Borisov gave us our first direct look at material from another star system, and it looked remarkably similar to comets in our own solar system. These interstellar visitors remind us that the space between stars is not truly empty. It is populated by wandering objects, debris from other solar systems, and perhaps things we have not even imagined yet. The Oort Cloud is connected to this broader interstellar environment. It is the boundary zone between our solar system and everything else. Let us also spend a moment thinking about the philosophical implications of what we have discussed. Throughout human history, we have gradually learned that we are not at the center of anything. Earth is not the center of the solar system. The Sun is not the center of the galaxy. The galaxy is not the center of the universe. We are ordinary in the cosmic sense of the word. But ordinary does not mean unimportant. The fact that we exist at all is remarkable. The fact that we can understand the universe even partially is extraordinary. We are the universe becoming aware of itself. That might sound like a grand statement, but it is literally true. The atoms in your body were forged in ancient stars. The iron in your blood was created in a supernova. You are made of stuff, as Carl Sagan famously said. And now that star stuff has organized itself into a form that can think, wonder, and explore. We send spacecraft to distant worlds. We build telescopes that can see the edge of the observable universe. We write equations that describe the behavior of matter and energy. We are small, yes, we are fragile, but we are also capable of understanding things far beyond our immediate experience. That is the gift of consciousness. We can imagine places we have never been. We can think about times before we existed and after we are gone. We can contemplate the Oort Cloud, the dark matter halo, and the cosmic rays without ever leaving our living rooms. Our minds can travel where our bodies cannot. As we conclude this journey, I want to encourage you to carry this sense of wonder with you. The universe is not a cold, distant thing. It is our home. We are embedded in it, connected to it, made of it. When you look at the night sky, you are looking at your ancestors and your descendants. You are looking at the raw material from which you were made and to which you will one day return. What lies above and below the solar system is not separate from us. It is part of us. The Oort Cloud objects contain water that might have once fallen on Earth, becoming the oceans that gave rise to life. The dark matter that surrounds us helped create the galaxies where stars and planets could form. The cosmic rays that rain down on us are messengers from the distant cosmos, connecting us to events billions of light years away. We are not isolated. We are not alone. We are part of a vast, interconnected web of matter and energy that spans the entire universe. And every time we learn something new about that web, we learn something new about ourselves. So keep exploring, keep questioning, keep looking up. The universe is waiting for you above and below in every direction. There are mysteries to solve, wonders to discover, and adventures to have. The journey never ends. It just keeps getting more interesting. Thank you for being part of this journey. Thank you for your curiosity and your attention. People like you are the reason we keep exploring, keep learning, and keep pushing the boundaries of what we know. Hit that like button, subscribe to the channel, leave a comment telling me what blew your mind the most. Share this video with someone who loves space. The universe is vast and strange and beautiful. And so are you, because you are part of it. Never forget that. What lies above and below the solar system? Everything you could ever imagine, and more. Go find out for yourself. The cosmos is calling. And before I truly let you go, there are a few more incredible facts I want to leave you with. These are the kinds of details that stick with you long after the video ends. Did you know that the Voyager spacecraft are still transmitting data back to Earth? Their signals are incredibly weak by the time they reach us, about 20 billion times fainter than the power needed to operate a digital watch. And yet, our deep space network can pick up those whispers from across the void. The dishes we use are about the size of a football field, and they can hear Voyager's faint call from more than 14 billion miles away. That is a testament to human ingenuity and our determination to explore. The golden records aboard both Voyager spacecraft contain sounds and images from Earth. A message in a bottle thrown into the cosmic ocean. There are greetings in 55 languages. There is music from Beethoven and Chuck Berry. There are images of people, animals, and landscapes. The records are our introduction to whoever might find them, millions or billions of years from now. Voyager might outlast everything else humanity has ever created. Let us also think about the future of our solar system in the context of the galaxy. Right now, the Milky Way is on a collision course with our nearest large neighbor, the Andromeda Galaxy. In about 4 to 5 billion years, the two galaxies will merge. This sounds catastrophic, but individual star collisions will be rare because the distances between stars are so vast. Instead, the galaxies will pass through each other, gravitationally disrupting their shapes, before eventually combining into a single, larger galaxy. When this happens, the night sky will look completely different. The neat spiral structure of the Milky Way will be gone, replaced by a chaotic jumble of stars. New star formation might be triggered as gas clouds collide. Our solar system will be shuffled around. possibly ending up in a completely different part of the merged galaxy. The Oort Cloud will be profoundly affected by the galactic merger. The gravitational disturbances will scatter many Oort Cloud objects, sending them flying in all directions. Some will fall toward the inner solar system. Others will be ejected into intergalactic space. Let us also consider the role of supernovas in shaping the space above and below our solar system. Supernovas are the explosive deaths of massive stars, and they have profound effects on their surroundings. When a star explodes, it sends shockwaves rippling through the interstellar medium, compressing gas and triggering new star formation. It also spreads heavy elements into space, enriching future generations of stars with the materials needed to form rocky planets. The local bubble that our solar system currently inhabits was probably carved out by multiple supernovas over the past 10 to 20 million years. These explosions swept away the surrounding gas, creating a low-density cavity hundreds of light years across. Supernova remnants are also sources of cosmic rays. The shock waves from supernovas can accelerate particles to enormous energies, turning them into the cosmic rays that bombard our solar system. Every time you are hit by a cosmic ray, you are feeling the echo of an ancient stellar explosion, a message from a dying star delivered across light years of empty space. The nearest recent supernova remnant to our solar system is called the Geminga pulsar. This is the spinning core left behind after a massive star exploded about 300,000 years ago. Geminga is only about 800 light-years away, which is close in cosmic terms. Even closer encounters with supernovas might have happened in the past. Some scientists have found evidence of supernova debris in deep ocean sediments, layers of rare isotopes that could only have been produced in a stellar explosion. These isotopes suggest that a supernova occurred within a few hundred light-years of Earth about 2 to 3 million years ago. The relationship between cosmic events and life on Earth is a fascinating area of research. We tend to think of life as something that happens on our little planet, isolated from the rest of the universe. But the truth is that we are connected to the cosmos in profound ways. The elements in our bodies came from stars. The cosmic rays that hit us come from distant explosions. We are not separate from the universe. We are part of it. This cosmic perspective can be humbling, but it can also be inspiring. We are small, yes. We are vulnerable, but we are also resilient. Life has survived on Earth for nearly 4 billion years, through ice ages, asteroid impacts, volcanic eruptions, and mass extinctions. And now we stand on the threshold of a new era. We have the technology to leave our planet, to explore other worlds, to peer into the depths of space and time. We are becoming a spacefaring species, taking our first tentative steps into the cosmic ocean. What lies above and below the solar system is not just something to study from afar. It is our future. The resources of the solar system could sustain humanity for millions of years. The knowledge we gain from exploring space could transform our civilization. So dream big, think long term. Imagine a future where humans have settled the Kuiper Belt, where we mine the Oort Cloud for water and organic materials. These things might seem like science fiction today, but so did landing on the moon just a few decades before we actually did it. The universe is vast and full of wonders. Above and below our solar system, there are mysteries waiting to be solved, places waiting to be explored, discoveries waiting to be made. Never stop wondering, never stop exploring, never stop looking up at the stars and asking what if. The cosmos is calling, and it is time to answer. Thank you for joining me on this incredible journey. This has been a look at what lies above and below our solar system. I hope it has expanded your mind and filled you with wonder. Remember to like, subscribe, and comment. And most importantly, remember to keep looking up. The universe is waiting for you. Clear skies, safe travels, and may your curiosity never fade. Until we meet again among the stars, my dear friends. Goodbye for now.